back here. Going to talk about our last two examples of series. The sum n equals 0 to infinity of 0.8 to the n, and the sum n equals 0 to infinity of 1.08 to the n. And to talk about this, we will generalize a little bit and talk about geometric series in general of the form the sum, and I'm going to use k equals 0 to infinity of x to the k. We'll look at this for different values of x. Okay, so the partial sums here, the nth partial sum, p sub n, is equal to the sum k equals 0 to n of x to the k, which is 1 plus x squared out to x to the n. So if we want to find a shorter form of what that is, well, we can look at x times p to the n. Alright, so we're going to multiply each term by x, so that raises all the powers. So now we have the sum k equals 1 to n plus 1 of x to the k, and that is x plus x squared plus, keep going, and I'll have an x to the n, but then I multiply the previous x to the n by x, and I get x to the n plus 1. And now I can subtract these two things, and I get p sub n minus x times p sub n, and that's equal to, if I look here, I have 1, and there's no 1 to cancel that on the bottom, but I have x minus x, so that cancels, and x squared minus x squared, and that cancels out to x to the n minus x to the n, and that cancels, and so I'm left with a minus x to the n plus 1. Now if I factor p sub n out on this side, I get p sub n times 1 minus x equals 1 minus x to the n plus 1. And so p sub n is 1 minus x to the n plus 1 divided by 1 minus x. Okay, so that is the nth partial sum. It gives us a nice easy form if you want to add the first n terms of a geometric series. Alright, now if I want to find, I'll call this sum of the series equal to p. Alright, and so p is the limit as n goes to infinity of p sub n, which is the limit as n goes to infinity of 1 minus x to the n plus 1 divided by 1 minus x. Okay, and so when does this converge? Well, if the absolute value of x is less than 1, then as we raise x to higher and higher powers, those powers go to 0. So our series, or our sequence of partial sums, will converge, that's an R, to 1 over 1 minus x. If the absolute value of x is greater than 1, alright, then the powers of x are going to get bigger and bigger, so this is going to get bigger and bigger, meaning this sum is going to get bigger and bigger, because again 1 minus x is going to be positive, and so while this, or it's going to be negative, so while this gets more and more negative, I'm going to have negative over negative, which is positive, and regardless the series is going to diverge. Now if x equals 1, alright, well, we're adding up power 1 a bunch of times, and that is certainly going to diverge. if x is -1, okay, then what's going to happen? Well, we're going to add 1 minus 1 plus 1 minus 1 plus 1 minus 1. And in the long run, what's going to happen there? Well, p sub n is going to be 1 if n is even, and is going to be 0 if n is odd. Well, this is an alternating sequence. It does not converge by our definition of converging, so the entire series diverges. Okay, now this is, if you remember the video we watched in class on the first day, all right, there's a difference in the divergence here and the divergence up here. This does not go off to infinity. It alternates between 1 and 0, okay, versus these go off to infinity. Now, the physicists who were doing our little video wanted to argue about what this should be, and if you have a different version of what it means to converge, you can get what they got, which was that this sums to -1/12, and that leads to all sorts of conundrums. But by our definition of converging, which means a series converges if its sequence of partial sums converges, this series does not converge. Okay, so now if we look back over here, wait a minute. If we look at our two examples, all right, the sum of 0.8, well, that's going to converge. The absolute value of 0.8 is less than 1. And it will converge to 1 over 1 minus 0.8, which is 1 over 0.2, which is 5. And the sum n equals 0 to infinity of 1.08 to the n will diverge. So we have convergence and divergence of geometric series. And we can see on our next slide that written out. We will come back and have another video where we'll talk about the ratio test and the root test, which are sort of variants of tests for series that are like the geometric series but not quite the geometric series.